All right, so basically my plan today is just kind of briefly talk about what kind of topics we've talked about in the class and what can be on the final. The final exam will be similar to homework and similar to the exams, midterm exams, in terms of the types of problems that are being asked. You'll get partial credit like you would in a normal exam in terms of how close you get to the final solution, what equations, what steps you take that are approaching the final solution will get you more points. I have had some questions on my grading scale, so I want to go ahead and kind of lay that down here. So basically, an A would be 90 and above, no stricter than that. A B plus is going to be 88 and above. A B is going to be 80 and above, and so on. So that's going to be, there's going to be no stricter than that. So plus, I don't give minuses, so there, you can't get a B minus. If you have 80 and above, you're going to have a B. There may be a curve this semester. I don't know for sure. I'm going to wait until see what the final grades are before I decide whether or not to curve. I have not curved in recent semesters, but this is the first time we've done online exams, and so that might warrant a more of a curve to get the grades where I want them to be. But I wait till the end to do that. So if you're concerned about your grade, probably the best step would be to take the final. Of course, assuming, well, I guess either way, you probably want to take the final. And then once the final exams are in and graded, then I'll be able to take a look and see how the whole class is sitting and see if a curve makes sense. But yeah, the exam scores are currently lower than I would have hoped for on exam 1 and exam 2, and we'll see what happens with exam 3. In the past, exam 3 usually has been one of the higher scoring exams, but it's harder to predict with the online exams. So any questions on the grading scale? Yeah. An 89 would be a B plus. Probably. I mean, I do look at the boundaries a little bit. Now, 89 is pushing it in the boundary. 89.5, for example, that would be something that, assuming there is no curve, or if there was a curve, it's still the same thing. I'd be looking afterwards at something like that. Because what the curve would most likely be, I've done it several different ways in the past, but one way I've done it is I just add a certain percentage point to everybody's final score to kind of bring everybody up. I've done one where I've normalized in some fashion with respect to one of the scores, trying to be more creative in how you curve it. Anyways, so it's been so long since I've done that, I'm not sure. But anyways, we'll just assume that the curve, whatever it is taken into effect. So if you're sitting at 89.5, then the kind of things I look for to see whether or not you really deserve an A was, did you have one bad exam? Did you do pretty well in the course, but you had one bad exam? And the easiest way for me to assess that, honestly, is through the final exam. I mean, if you got an A on the final exam, then that tells me you really knew the material. It's just you had a bad exam, or maybe several bad exams or something, depending on how all the points lie. If you choose not to take the final exam, that does not mean I don't make that same assessment. It's a little bit harder. So here in this case, I'd go back and I'd look at what the attempts were. Maybe I'd look at what numbers you were putting in to see if I could figure out what your thinking was, which is really hard at just looking at numbers. The other thing I look at is, were you turning in the homework consistently? Was your labs submitted and your homework submitted on time? That would kind of judge a little bit about, what is an 89.5 is, should I move that cutoff down from 90 to 89.5? It's a hard assessment to make, and usually there's 4 or 5 or 6 or more students that are going to be in that same range, then I'm going to have to look at all of them. And so sometimes it's a bit of a judgment call. Inevitably, no matter where I decide to make the cutoff, no matter what, I'll always get emails from students saying that they worked hard in the class and they really knew the material and they really deserve the next higher grade. That's probably true, but I have to draw the line somewhere. So if you happen to be below that line, sorry, but I do have to draw the line somewhere, because literally I have students within 0.1%, usually from starting somewhere in the A's all the way down to somewhere in the C's or D's, and then they start to have usually a larger spacing between students. But yeah, so I don't usually change grades based on getting an email saying that you worked hard. I'm assuming you're all working hard. It's just I have to draw the line somewhere. So if you miss the cutoff, sorry. I just had to make a judgment sometimes. And that's never an easy decision to make. I'd rather, though, have it where I can make that judgment and make it so I can look at grades and try in some way to, make a call than just having a sharp, firm cutoff where if you have an 89.99, you get a B plus no matter what. I'd rather have the opportunity to look at performance and see if there's one bad exam or, you did everything right, but you turned in a homework late or something. I guess you can't turn in homework late, so you missed a homework problem or, you forgot to do the quiz one day or something. And I do actually search through my email sometimes and see, okay, was, the students missing this quiz? Was it just they were working on their homework and forgot to submit it and, just totally spaced it for 3 days? That might be, reason to think, okay, well, maybe it was just a fluke. But on the flip side also, like I said, if you've done all the homework, you've done all the exam or all the quizzes and things, I don't know. It's a very hard judgment to make. So anyways, I hope that probably muddies the water, but yeah, so that's how I do the grading. But yeah, if you're like sitting at an 85%, then no, that's not close to a B plus. I think I have gotten emails from students who said that, you'd look at this since if I was close, and I'm like, yeah, but you're at 85. That's not. Yeah, if you were at, 87.5, then yeah, I would have given you a B plus because of those arguments, but not 85. So, all right, so material covered on the exam. Well, first, the exam will be in here. Hopefully I got the room number right, but it's in here. We'll make use of our room. It'll be on Monday, December 12th from 2:15 to 4:15. I have not gotten anybody requesting to do an online exam, and that meaning an online final exam, which isn't really surprising. So unless I get an email before class is over, there will be no option for an online final exam. You have to take the paper-based final exam, and you're all very disappointed with that, I'm sure. So that's when it will be. Obviously, exam 3, do not forget exam 3. It is online. You have to do exam 3. If you don't do exam 3, then you can't make up those points in any way. So it is online. Exam format for the final will be 4 problems. It could be 4 problems with a part of some of them having short answer type questions, or it could be 3 problems that are relatively computationally intensive, and 1 problem where I have a collection of short answer covering a variety of topics. Similar in format to some of the quizzes, although usually I have more things that you can write because it's written. So I'm not restricted to multiple choice or matching or true false. I may do a true false, but if I do a true false on a written exam, I always ask why and have you try to explain something. It is closed book, closed notes. You are allowed to bring let me be very clear on this. You're allowed to have a formula sheet which will be provided with the exam. Do not bring your own formula sheet. It'll be provided. And you're allowed to use a calculator. And you should show all your work for full credit. All your work reasonably for full credit. You don't have to write down every step of your algebra or something if you just type it in your calculator and solve it. Now, if you are solving it completely by hand, then yes, write down every step. But if you're solving some part in the calculator, just, you can say solved in calculator, or just I can kind of assume that sometimes. But don't just have an answer randomly showing up. If the magic fairies told you the answer, get it notarized or something. Have them sign their name or whatever. Anyways. So the course objectives. So these are the main themes that we covered in this course. Be able to solve for currents, voltages, and powers for circuits containing resistors, inductors, capacitors, transformers under single-phase, steady-state sinusoidal excitation. Be able to solve for currents, voltages, and powers for a simple balanced 3-phase circuit. Be able to relate currents and voltages to mechanical motion for both DC motors and DC generators, and be able to relate currents, voltages to mechanical motion for both AC motors and AC generators. And at one time when I gave a final exam, I tried to have 1 problem match up with each of the course objectives. Now I tend to be a little bit more flexible on some of that. So in general now, 1 problem will match up from the material from homework 1 and 2, one problem will match up from the material from homeworks 3 and 4, one problem will match up from the material from homeworks 5 and 6, and one problem will be whatever else I want. So I've had exams where I have one question on shunt and one question on series DC motors, and then I have an AC circuit type question, and then I have an AC motor type question. I've combined my AC circuit and AC motors, as you saw in the example final I did earlier, in some fashion, and then had another AC circuit, another AC motors problem. So in that case, it's almost like 2 AC motors questions, and then I had a series connected DC motor, I believe, in that case, and the transformer. I guess it was a transformer question was the other one in that one. So I can mix and match a lot. I don't try to necessarily test everything on the final exam. I try to be a bit more selective and make it a little shorter. I also should say that I used to have 5 problems on my final exam, and I decided to scale it back to 4. But because I decided I didn't have to try to test everything we covered in class. I could pick and choose a little bit. It makes a shorter exam, get the same impact. I don't anticipate the exam lasting 2 hours, and that's the amount of time you have for it in class, necessarily. Now, usually whenever I say that, the students, they work on the exam the full 2 hours, most of them. But it should not take that long to work it through. So time will not necessarily be a complete deciding factor. It will be a factor depending on how fast you're able to work it, but usually in the past, if I have a 2-problem final or 2 problems in the midterm type of setting, I expect that to last about 35-40 minutes. And so I would expect these 4 problems to take you about hour, 20 minutes, hour and a half, somewhere in that time frame is what I would expect. But you have the full 2 hours. And that's typical. That's a student who knows what they're doing, and they're able to crunch through it. Now, some students could actually work it faster and be done in an hour, but that's kind of the typical thing. So usually I try not to make time be a major factor in my in-class exams, but it varies a lot depending on how well you know the material, and if there's something that's being asked and it's just not clicking. Like I think one of the problems on the first midterm, there's something with gear ratios and finding the efficiency. I know from students' comments coming back to me, they got lost as to exactly how to translate what I was putting in the question to what they were supposed to solve for. And it was a relatively simple little step translating between, gear ratio, finding out, doing like you did in the homework where you find the most efficient torque and then translating that torque to a gear ratio by having your torque coming out of your motor and the torque you need, and then that rate, dividing those two gives you the gear ratio. Something like that on the final exam can sometimes eat up a lot of time because students can know how to solve it, but they're just staring at it and they're not seeing some little piece of information. And sometimes they get it eventually by staring at it, and sometimes it's just not a good day. But that's the kind of thing that can take up more time. Anyways, I'm going too slow here. But DC machines, so we talked about linear motors for a while, and motion of the linear motor, and we'll know whether motor or machine is acting as a generator or a motor, and the basic operation of a railgun would be some of the stuff that we talked about there. The role of a commutator in a DC motor is important. Make sure you know that. Given the magnetization curve and the equivalent circuit for a DC motor, be able to find the voltage, currents in the circuit, the speed, torque supplied. Basically, be able to solve for DC motors in series and shunt configuration. Also be able to explain how R adjust controls the speed in a shunt connected DC motor, or if I say the R adjust goes up, what happens to the speed of the motor, or R adjust goes down, what happens to the speed of the motor. Those are the kinds of things that you want to be able to know. Be able to identify whether a motor is shunt connected DC motor or permanent magnet DC motor, or conversely, a series connected DC motor from the speed torque curve, or vice versa. So the kind of thing I could ask you in a exam is I could tell you, sketch the speed torque curve for a series connected DC motor. Or I could show you a speed torque curve and say, is this a series connected DC motor or shunt connected DC motor or what? And then you would have to explain which one it was. Be able to select the best motor for a given application. You saw an example of that when we were doing the practice final. I had a matching thing there. Usually I try not to make that too complicated. on one hand. On the flip side, sometimes I'll ask something where it is a bit open-ended, meaning you could probably argue that both a series or shunt-connected DC motor or permanent magnet or something would work in a particular application. And there I'm more interested in looking at what is your thinking, what is your logic. So if you pick one, if it doesn't seem to be clear and you pick one, just make sure you explain it well what you're thinking, because that may be where I'm putting most of the points. And know that the shunt-connected DC motor has approximately the same speed when it's operating its normal operating range, regardless of torque. Not exactly, just close. It does slow down. You have to be able to take that into account. You have to be able to calculate that. So it just gives you a ballpark figure, not the one that's necessarily in the computational problem. But just know that that's kind of how it works. Whereas the series connected tends to slow down at higher torques. Given the magnetization curve and the equivalent circuit for a separately excited DC generator, as well as the rotational speed from prime mover, be able to find the voltage, current, circuit, so on in that case. Be able to determine how the field circuit of a separately excited DC generator might need to change with the load to maintain some output voltage, so how to tweak the magnetic field. And be able to determine the voltage regulation for a DC generator, and that was in some of the homeworks. Stepper motors, be able to explain how a stepper motor functions, how it works. So if I say, how does a stepper motor work? Be able to tell me. Given the desired speed and torque and the speed-torque curve for a stepper motor, be able to determine if the motor will work or stall. And remember, that was in the lab. That was something you did in the lab. Occasionally, I will pull things in that you've done in the lab. And it's easier for me to do that on a final than it is on the midterm exams, because when the lab is offered, it might be a little bit delayed because I don't want to cover stuff in course before or have you see it in the lab too much out of sync of when you've seen it in the course. And so asking something like that you've done now in your lab, I could put on a final exam because you've done it in your lab. Be able to calculate the number of poles for a given step or step size given the number of poles. There's a homework problem on that. Be able to calculate the pulse rate to rotate the motor at a desired speed. Be able to calculate the spatial control for given the screw pitch and number of phases and the number of poles. That's another example of something that threw people off the first time it showed up on a final exam. Is I put, oh no, I'm sorry, that wasn't a final exam question. That was a homework question. First time I put that one homework question on, seems to give students less trouble now. A lot of students didn't know what screw pitch was. And even now, a lot of times students don't know what screw pitch is. So make sure you know what screw pitch is for the stepper motor type problems. I think you know what screw pitch is, you just may not think of that term a lot of times when you're working this. Be able to write the phasor representation of a current or voltage from time domain expression or vice versa. Be able to find the complex impedance for a set of inductors, capacitors, and so on in a circuit. Be able to find the values of inductors, capacitors, resistors, and frequencies so that the complex impedance satisfies certain properties. That's, current, voltage in phase, power factor of 1. That's the kind of thing I was after with that. Be able to solve for currents and voltages in the phasor domain using Ohm's law. Be able to solve for currents and voltages in the phasor domain using node voltage. You'll find the time average power, reactive power, apparent power, and all those from the phase information. Now, one thing that is critical for the final exam, very, very critical, is remember, I give a lot of points for knowing time domain and phasor domain. So if I ask for something in the time domain, even if you have no clue how to solve it, write down some random expression that's in the time domain and say, this is what the time domain looks like. I have no idea how to solve this problem, but this is the time domain. And you can get half the points on that part of the problem just by doing that. So take advantage of that, because I will most likely be asking you a problem where I say, what is ... in the time domain? Or solve for this voltage in the time domain. Much more challenging to do that on online exams. Phasor domain, same thing. It's not worth quite as many points, but I can do that. I can say, solve for this current or whatever in the phasor domain. And then, even if you can't solve for that current, give me something in the phasor domain and make sure it's correct in the phasor domain, circle it and say, this is phasor domain, and then you can get the points for that. Now, units, remember, the units were very important and very confusing with powers. So you had the time average power has units of watts. The apparent power, and has units of volt amps. The reactive power has units of volt amp reactive, or VAR. And so one of the things that I tend to do when I'm grading exams is most of the time units are not worth a lot. They may be worth some. But when I'm talking powers, they are worth a lot. So I might have 1 point associated with having the number right for the power, and 2 points associated, or 3 points associated with having the units right, because the units is a way of communicating what power you're talking about. So that's another one where you can get easy points, even if you can't get your math right. If I say, what's the time average power? Well, put down watts. If I say, what's the reactive power? Put down volt amp reactive. Even if you don't know how to find it, put down volt amp reactive, and that'll get you 3 points, potentially, or 2 points. So take advantage of showing me what you know. Be able to find the time average power, reactive power, all that stuff from phasor voltages and currents as well. So both time domain and phasor domain. Know the parent power is a volt amp capacity required to supply the average power. That's one of the things we defined with the parent power. Be able to use the power quantities to find other parameter circuits such as the phasor relationship between voltage and current. And we did a little bit of an in-class example on that where you had the power factor and you had, I think, the time average power or whatever. Anyways, or maybe it was you had, I guess here I'm thinking, you know, if I tell you the apparent power and I tell you the time average power from there, you can get the power factor. The power factor, you can find the inverse cosine of theta v minus theta I. You may not know whether theta v or theta I is, which one's greater, but you can at least find that. Be able to solve for the currents and voltages and powers in a circuit with only ideal transformers, resistors, and independent current/voltage sources. And so here, phasor domain circuit analysis. Usually my transformer problems, not always, but the vast majority of the time, my transformer problems do not have any reactive components to them. They only have resistors and transformers. Occasionally I might stick something else in there if I'm trying to assess something. But that's usually what they have. Whereas the other circuit components, of course, will have complex terms. Be able to solve for currents, voltages, and powers in a circuit with non-ideal transformers and resistors. Now, non-ideal transformers, it's much more unlikely for me to give you a non-ideal transformer problem because it's so long. It doesn't necessarily test, in this case, your idea or your knowledge of a transformer because you spend so much time trying to work through all the algebra of all the complex numbers. So it's possible to show up, but not very likely, because if it did show up, then I have less time, because I'm very mindful of time on these exams, to ask you something else and assess maybe your knowledge in something else. So I don't think I've ever had a non-ideal transformer problem on a final exam with one exception. And that is when I put something in there that was at DC. So I had a non-ideal transformer with a DC source connected to it, and I said, find the power delivered to the load. Remember, if I say DC, no power gets to the load. You're done in 2 seconds. Not 5 pages later, which some students did. That was fun to grade. No, actually I didn't. That was not hard to grade at all because they didn't see it was 0 watts, so they ended up losing most of the points. Although I guess there was a few students, there was like 5 or 10 students who, after doing 2 or 3 pages of work, I don't know how they had the time, but anyways, solving this non-ideal transformer problem, they correctly got 0 watts coming out. Because in the non-ideal case, you have all the inductors in there that short out, and so it goes to 0. Anyways, so yeah, I give them full credit. I don't remember if I added a little note. I guess I didn't because it was final. But I think I wanted to add a little note saying, there's a shorter path. Anyways. So yes, that's the only time I've had a non-ideal transform problem. Balanced 3-phase circuits, be able to solve for currents, voltages, and powers in a balanced 3-phase circuit for a voltage source for each phase and complex line and load impedances. So be able to do any of these. Most of the time, if I give something, it is going to be a delta-delta configuration, which you have to convert to a YY most of the time to solve. Be able to convert delta-connected source to Y-connected source and vice versa. Be able to connect a delta-connected load to Y-connected load and vice versa. So be able to solve those. AC machines. Be able to explain how the rotating magnetic field in a 3-phase induction motor causes the motor to spin. Know what is meant by slip for the AC induction motor. Be able to calculate how many poles are needed on a 3-phase AC induction motor to have it turn at a given speed. So once again, being able to, if I tell you that the speed is such and such and the frequency is, 127 hertz, then what is, excuse me, what is the most likely number of poles? So you want to be able to calculate that. Be able to calculate the slip and the frequency of the induced currents in the rotor bars given the number of poles and the speed of the motor. We don't do as much with frequency in the rotor bars anymore, but definitely want to be able to calculate the slip. You use slip almost on all these problems. Be able to calculate the new speed of a 3-phase induction motor given the change in torque or power, assuming that the motor is operating in its normal operating range, where slip is proportional to torque. I can almost guarantee you that you're going to need that on the final exam. In some way, I almost always ask that, slip is proportional to torque. Might be helpful for exam this week too. Be able to calculate the impedance, power factor, line current, output power, copper losses, output torque, efficiency, all that fun stuff for the AC motor. Now, once again, I have to balance this. Remember on the homework that's due this week, it was like, I don't know, 2, 3 problems, depending on how you want to, I guess it was 2 problems, 2 long problems, is that. And once again, that becomes a little longer on a final exam. Now, I can still do it, or I can still do parts of it, like that example final I showed you. You were calculating the impedance, I think, or something, and some VX and stuff in there. So I can still do it, but I'm more limited. And so here, for example, I'm implying you could go all the way to a 3-phase circuit where you have line impedance and everything else, which would make the problem really long. And that's longer than what would be intended. And so that example final is probably a good idea of some kind of things that I could ask along those lines. Be able to find the starting torque for a 3-phase AC induction motor. Once again, you did that in the homework, but that was a relatively long process. And so you have to be mindful of that. And so once again, take a look at that example final that I worked. That would probably give you the best idea of the kinds of things I could ask along those lines. Be able to explain the basic operation of a synchronous generator. Once again, that's the kind of thing I could just ask. I can say, how does a synchronous generator work? And then I expect you to explain it. Be able to calculate electrical frequency generated by synchronous generator given the rotational speed of the generator. All right, so those are the topics. Obviously, there's a lot of things we've covered. I'm not going to be able to test you on everything that I was given here. And so sometimes it's debatable as to how helpful this is. It doesn't exactly give you a lot of hint, but I think, honestly, this time at least, that practice final will allow you to relate some of the things that are said into what has kind of been asked in the past. In some way. I mean, obviously, it's going to be a different test, so it's not going to be identical, but you can see kind of things that I like to ask, how long the questions tend to be. So any other questions? Yeah.
You open up lectures after Friday, some of the topics, so we have to start.
Yeah, I should be able to do that. If they're not open, could you send me an email on Saturday, and then I can open those up. Now this particular lecture I'm going to post on YouTube, and I don't think I'll try to post it twice. But yeah, the others, yeah, I can open them up again after Friday night. I'll try to remember that, but if they're not there by Saturday morning, just send me an email and I'll make sure to get them up right away. Yeah.
Okay with you if program some of these our graphing calculators? Number crunching go faster.
Well.
Especially with the complex equations using complex.
Well, I'm not going to check everybody's calculator to see what they have programmed in. So I guess so. That's one of my concerns with calculators, is some of them can get so, advanced. They can do lots of things. So yeah, I guess that would be okay. Yeah, I have no way of telling whether or not you did it, so I guess I might as well say you can do it. Better to ask permission than get forgiveness or something. Anyways, I don't know. Sometimes it's better to get forgiveness than seek permission, but that's only when you're dealing with a bureaucracy. So any other questions? Yeah. Last problem of the first homework. Yeah, let me pull that up. I don't even remember what that one was now. Okay, so on the last problem of the first homework, which many of you may have not looked at any, since I've even looked at it. So you're given a voltage, a shunt-connected DC motor, you're given R adjust, and RA and RF, so you have all the resistances. The motor has negligible rotational losses, so you don't have to worry about that. And you want to plot the efficiency versus torque, assuming no rotational losses. Now this problem is actually relatively important, because one of the most important aspects when you're working with a motor system is how do you make it efficient. In fact, if you look at GE motors, a lot of times they're very interested in operating their motors in the most efficient range possible and designing more efficient motors. So understanding when it's efficient is probably one of the most important things to calculate, even if this problem was a pain. So what is the most efficient torque, and what is efficiency at this torque? And so first we have to find K phi, and I won't go through that for sake of time here. So you've given the magnetization curve, you find the field current from VT and RF and R adjust, and it turns out to be 4 amps in this problem. And then you use that to get K phi, and K phi ends up being 0.9549 Weber. So that's your K phi. And so now you want to find your efficiency. So your efficiency is going to be your developed power all over your input power times 100. And your developed power, of course, is going to be your speed, which is going to be omega m. And omega m is going to be Vt all over K phi, which you know, minus Ra, which you know, all over K phi squared, which you know, times the developed torque. And I want to express this in terms of torque because I want to find the most efficient torque. And so to do that, it makes sense to work from an expression that is only based on torque. So this is my speed, and I need to multiply that by the developed torque to get my developed power. And I'm not going to bother rewriting that 100. Yes, I should be multiplying by 100, but the most efficient torque doesn't matter if I multiply by 100, and I'm running out of room. So, and then I have to have my input power. And my input power is going to be Vt times the current that is flowing out of the DC source. And the current flowing out of the source is going to be my field current, which I already found when I was finding K phi, plus the current that is flowing into the IA, the armature current. And so from the formula sheet, we know that this is going to be equal to torque developed divided by K phi. Because the developed torque is going to be equal to K phi times IA. And so this term right here is my IA. And so there I have an expression relating the developed torque to the efficiency. Now I need to find the most efficient torque. Probably the best way to do this quickly is to actually graph it. The other way to do it is to take the derivative, which you can do. It's easier if you have numbers plugged in rather than what I have with all these variables. And so then you would take the derivative of the top times the bottom minus the derivative of the bottom times the top divided by the bottom squared. And if you do that, you end up with Vt over K phi minus Ra over K phi squared times 2 times the developed torque. So that's the derivative of the top. And I need to multiply this by the derivative of the bottom, or excuse me, by the bottom, which is Vt times If plus the developed torque divided by K phi. So that's the top times the bottom. Then I have minus the top times the derivative of the bottom. So that would be minus Vt over K phi times the developed torque minus Ra divided by K phi squared times the developed torque squared times derivative of the bottom, which is just going to be Vt over K phi. And then this whole thing has to be over the bottom term, which would be Vt times If plus torque developed over K phi squared. And this you would set equal to 0 in order to find your maximum. So obviously one trivial solution would be torque being infinite, which is not going to give you obviously a maximum. And so that means you can multiply through by that bottom term, so it cancels out, and you're just left with setting this term in the numerator equal to this term in the numerator and solving that. And you can see, now here I have a torque developed, here I have a torque developed, so this is going to be a quadratic in developed torque. And then here, of course, I have a developed torque. So this expression, when I set that equal to 0, is going to give me a quadratic term in terms of the developed torque. And so let me go ahead and write what that quadratic is. And so that would mean 0 would have to be equal to Ra times the developed torque squared all over K phi squared plus 2Ra torque developed all over K phi times IF minus Vt squared all over R adjust plus RF. And I apologize, I think I switched my notation. When I was working it through in my solutions, I didn't write it as IF, I wrote it as Vt over R adjust plus RF. So my solutions are even longer. So here, this term was really Vt times IF. That's what that would be. And so this is a quadratic in terms of torque. You can solve it. You end up with two values. In this case, you end up with one that's minus 30-something Newton meters, and then the other one's 23-something Newton meters. Obviously, you want the one that's 23 Newton meters. And when you then plug all those numbers back into the original expression, you're going to get an efficiency of about 75%. And so on the exam, you would do exactly the same steps. That was, if you were the one that you were asked to find the gears ratio, the only difference is when you're all done and you got your torque developed, well, you have your developed torque divided by your, I think your output torque that you were given, that would give you your gears ratio that you would want. So that was the only change on that exam. But could be a challenging change to see sometimes, especially in an exam. So any other questions? I know I went through that a little bit fast. I kind of assume that students have a calculator that can graph, so like this problem on the exam, I assume students would actually solve it by deriving this and then graphing that as a function of torque. That's kind of how I expected students to solve it. Make sure you bring spare batteries. I have never given a final exam where the batteries in somebody's calculator didn't die. I don't carry spare batteries. Maybe I should, but I never bothered to think to bring them. Usually a good Samaritan might help the student out, but that's not something you want happening during your test. So bring spare batteries, and if you don't use them in my exam, you'll have them for the rest of the week for your other exams. Something to write with is always good. I just realized something. I need to tell my TAs they need to help proctor the final exam. Oh well. I'm out of practice because I've given the online exams and was thinking online exams the whole time. Oh well, we'll send them an email and say, by the way, you have an obligation Monday afternoon now. Anyways. All right, so we'll go ahead and stop there and wish you luck.